Hi, now in this part of the video, in my last segment, we started working with the SpectraLine GP software. We actually set up all our configuration parameters, and then we initiated a count of a mixed gamma calibration standard source, which had basically cadmium, cesium, cobalt, and then we collected a spectrum for 600 seconds, which is about 10 minutes. Typically, a calibration spectrum should be counted for about half an hour, but because our count rate is sufficient, we counted for about 10 minutes. And now we have collected the spectrum, and now at this point we can see the spectrum is finished collection. What I'm going to do is I'm going to go ahead and conduct what we call is a peak locate and a peak fitting. So which means that I will identify all my relevant peaks in here, statistically valid peaks in here, and I do this by going to my processing, okay, and I go to peak search and I do a search with a fit. Once I do that, you can see that it does the calculations, and it has actually, if my fitting parameters were correct, it identifies all the statistical valid peak. If you come close, you will see that it's located my 88 keV cadmium peak, my cesium peak, my first cobalt peak, my second cobalt peak. Even though I did not have 1476 peak in my spectrum, I know there is a peak of 1460 keV from potassium 40 is picking this one up, and then the sum peak of these two cobalt peaks, which is about 2500, is showing up here. So I can see that it's pretty good right now, and it's picked up all the statistically valid peak. Again, going to processing, search, do a peak fit, and then it locates all the peak. At this point, I'm fairly happy with all the fitting that I have done. So for the sake of my records, in case I interrupt my work anywhere, I'm going to go ahead and save the spectrum, and I'm going to go ahead and save it to my LSRM work GCD 10175 data, and I'm going to call it test point source. I will say test disk 040117 spectrum, and you can see the spectrum files are saved in the SPE format. So that spectrum file I have collected now is saved. Now while I am working with it, I really have no need for the high voltage. So I can go into my configuration properties, I can go to my MCA, and I can go ahead and turn my high voltage off. And you can see the high voltage goes to 0 as it starts to ramp down here. No need to keep my high voltage on unless I'm doing another sample, because I'm going to use this spectra unless I don't like this spectra to go ahead and do my calibration and everything else. So now that I have conducted a peak search, I've saved my spectrum, I've located all the peaks, I am going to go ahead and do what I call is an energy calibration, because although my peaks are found, my calibration is slightly off. So I'm going to go into processing, and the first thing that I will do for my energy calibration is to go into energy calibration. Select energy calibration, and when you have already done a peak fit and you have located all the peaks, it lists all the peaks it has found. So my first peak it has found is at channel 485, which is this one. Second peak as channel 3646, which is this one. Third one at channel 6464, which is my first cobalt. Then the channel 7341, my second cobalt. Then my potassium 40 peak, which is here. And then it also calculated the peak, my sum peak, which is the sum of these two cobalt peaks at channel 3807. So what I'm going to do right now is I'm going to use these peaks and do an energy calibration. Now it is telling me that these are the approximate energies it thinks it is, which is fairly good. And part of the reason it's doing a fairly good job is because I also calibrated my MCA before I entered into SpectraLine from my WinSpec software. So my numbers are quite good, but I need to make them better for doing my spectroscopy. So I'm going to fine-tune these numbers by doing an actual energy calibration in here, which is what I also need to do an efficiency calibration and a nuclide identification. So I'm going to select my first peak, and then I will say what my energy should be by clicking here. We have two choices. We can actually go ahead and type this number in manually from our calibration standard sheet, which should be something like this, that you should receive. That will tell you what nuclides are here, what are the energies. Okay, and continue on. Or what you can do is, if you have the nuclide master option, you can also calculate you can read it from the library files that's already in here. So I'm going to use the library files in here because it also gives me an opportunity to show you what it is. So I will go in here, I will highlight this, and then I will go into my library, which is, if you go through these processes in here, it will tell you what these are. My library file is this one, and if you just go and highlight that without clicking on it, it will tell you what it is, and it tells you this is my current library. If I click on it, what it does, it actually opens up my library file in here. From here, I know that my first peak is cadmium 1809. And so what I will do is I will select cadmium from here. I will select it, and I will click on the plus bar to actually select the particular radionuclide gamma line that I'm interested in. I will highlight that, and I will simply click on my left mouse button and drag it and put it here. That's my first energy. Then I will highlight my second energy, which is my 660. Here is telling me 667, but we really know it should be around 661 keV, cobalt 60. But I'm going to use my library again here. I will go and highlight cesium 137. Click on the plus bar on the left side. Highlight that energy and put it here. Then I will select my third peak, which is the first peak of my cobalt 60, and find my cobalt 60 here, which should be somewhere down in here. It goes by the isotope number 1173 peak, and again. Then I go to the second peak of cobalt 60, my 1332 line, and again. Then I'm also going to use my fifth peak, which is going to be my potassium 40, because it's a good reference line since it showed up, even though I don't have potassium in my sample. Because I don't have a shielding around the detector, so more than likely I'll see potassium 40. If I had a shielding around it, I probably would not have seen that potassium 40 line. But it's a good line. The statistics is not bad. I'll select it. And if I want to do a calibration on the high side in here, I would have to know the activity of this sum peak, because it's a fictitious peak and it's not good because it's the sum of these two peaks. I am basically going to close my library now, and I will delete this line because I really don't want to use this sum peak. So what I will go in there, I will highlight that, I will right click, and I will say delete item. So now I am down to 1, 2, 3, 4, 5, which is sufficient. And now once I have selected that, I will bring this window to the middle, and I will try to fit these lines, these points that I have actually selected. And I do that by hitting the calibrate button. And it generates a straight line in here that shows you the calibrate button, but then it tells you something called a chi-square value. This chi-square value is best in terms of the error margin, in terms of fitting, when this number is closer to 0 or 1. So what I'm going to do is I'm going to try and do a refitting of this line by changing the polynomial equation that is in here by increasing the number of polynomials used for fitting. So from a polynomial of 1 with a chi-square value of 71.996, if I go to 2, the chi-square value drops to 4.022, which is quite good. But I can go to 3, I can bring it down to almost 0.0773. If I go to a polynomial of 4, I get a chi-square value of 0. From my understanding of the error propagation, the lowest chi-square value is good. So I'm going to take a chi-square value of 0 and accept the fourth order polynomial fit in there. And what I will do is I will save this calibration file because I like this fitting. So what I will do is I will save this calibration file, and by default it will show me what the calibration file was when I created it. So what I will do now is, instead of overwriting the calibration file that's in my data in here, I'm going to go to work, GCDD, data, And what I'm going to do is I will say that, but I will change the calibration file by number 1. I would say calibration new, and I will also say disk. And by default, if it's an energy calibration, the extension of this file is going to be .cen. So you don't have to put the CEN file. So instead of overriding my calibration file, I have actually created a new calibration. I have saved it. Now it is telling me, do you want to assign this calibration file to this particular detector? I said yes. And now we can also click here and say to use spectra, and that means that this is used for the spectrum that I'm going to call right now, and is going to call this calibration as the default calibration for my detector. So I am basically done with energy calibration right now. I can close this, and next I can do a shape calibration. A shape calibration basically tracks the energy calibration. Basically is a relationship between the channel numbers and the energy of the radionuclides. And a shape calibration basically tracks the shape of the peaks as a function of energy. From the physics of interactions, of photoelectric interactions, we know that at lower energies the peak tend to be narrower, at higher energies peak tend to be wider. So you can do a test and find out that if you look at the calibration, if you look at the full width half maximum value of a peak at 1332 keV, it's always going to be larger or wider than a peak at 88 keV. But for some reason I need to let the computer know how the shape of my peaks vary as a function of energy for this particular detector. So in the future, if I find two overlapping peaks and the full width half maximum value is bigger than what it should be based on my calibration parameters, then the software can go and do a backup calculations on the assumption that there is probably more than one peak in this location. So if you have a doublet or a triplet in one location and your peak is showing up as single peak, it's a problem when you have many radionuclides, which is abnormal in our case in environmental counting, but it can be in the case of, let's say, looking at the fluid coolant water where you have many short half-life radionuclides. In that case, the shape calibration becomes very important because you need to know the approximate width of the peak for your MCN detector at specific energies. This is the reason we do the shape calibration. So now I'll go to processing. Instead of going to energy calibration, which I have already completed, I will go to full width half maximum calibration. It brings up the plot. It shows me the peaks that I have used for energy calibration, and it will use the same peaks for shape calibration. And what I can do right now is simply go and say calibrate. And it will generate a straight line, but this line is not usually straight. It's usually a little bit curved, which means the shape of the peaks goes up in value, not linearly, but in some kind of a function that is a little bit slanted. So this is quite good as far as shape calibration number is concerned right now. The only problem that I see in here is that 1, 2, 3, 4, the fifth value which I have is off. And I can see why that is off, because that is my potassium 40 where I did not have much counts. So for the sake of that, I am going to delete this fourth value. And I am going to use only my cadmium, my cesium, and the 2 cobalt peaks to the shape calibration. And now I can go and play with the polynomial number to do the chi-square fitting. I can do a 3, and then I can see it's 0, which is the number that I would like to have for this fitting. Since it's 0, I will accept this, and I will save this calibration file. And again, instead of overwriting the default calibration file that we sent you in the GCD data file, I would go ahead and create a new one like my efficiency calibration called test 040117, and the default value is going to be .cfw, which is the full width half maximum calibration files, and I can save that. And then you say, do you want to assign this calibration to this detector? I said yes, and I will also apply this calibration to all the use spectra, and I will close it. Now I am ready for all kind of qualitative analysis, which means that if I find a peak, I should be able to correctly identify the energy of that peak. But I want to go beyond. I also want to be able to do a nuclide identification, for which I need to do an efficiency calibration. So in the next part of the video, we are going to show you how to do the efficiency calibration.